Alright, so this is IMO 2021, problem 2, an algebra problem. It's quite a hard one, actually. So we're looking at the solution to this. For this solution, we're going to prove it as a more general result, and then this will just be like a consequence of that. To get right into it, so I've prepared some things here already. Okay, so just have a few definitions need to get on the way before we properly talk about the first lemma we'll be using for this problem. Alright, so let n be a natural number, and we call this n the set from 1 to n. Okay, we denote it by a square bracket n, and then we define a function, or we consider a function mu from that set to plus or minus 1. So basically this is just like a sign, so I attach the sign to each of these numbers, and then so for any ij in z, we define alpha ij by three possible categories. So if I equal to j and then the range from 1 to n, then that gives 1. If I is bigger than j and they are within the range 1 to n as well, and we get 2 mu I times mu j, so that could be plus or minus 2. Otherwise we just get 0. So this just simply means that either we have 1 is less than or equal to j, less than or equal to I, less than or equal to n, or it's just 0. Then similarly we define wij in the same range, otherwise we get 0. We define it to be this sum squared. So this sum makes sense for this range because we're summing from j to I, so j has to at least be less than or equal to I. They could be equal, meaning we just have one term, and I definitely has to start from I and j have to range between 1 and n because we're taking mu of k, and that ranges from 1 to n. So the numbers from 1 to n are our main focus. Just to make the proof easier to flow, we just consider all integers. So that's why we have lots of terms being zeros actually. And then we look at a function h satisfying two properties. So it's a function from z cross z to r. Okay, so the first property is an inequality property, but it's not for all ij. We're only interested in this for I greater than or equal to j. So just similar to the range we're dealing with, except we're not bounding it between 1 and n anymore. And then h of ij is 0 outside the range of interest. So the range of interest is the one denoted by the green, so just call the green inequality. So the second condition is just simply saying is 0 outside the green condition. So this is the lemma we now want to prove, that if you take the sum over all possible i's and j of alpha ij times hij, we get greater than or equal to 0. Most of these terms are actually 0, just so don't look at this like an infinite sum. These are finite sums, because lots of the alphas and lots of the h, they're all 0 outside the range. They're all 0. So we actually have less than n squared terms here, at most n squared terms. Okay, so let's get into proving this. Once we've proved this lemma, then we'll try to apply it to a general class of functions that will lead us to our solution. Okay, so we'll prove this first. Okay, so to prove this, we consider what we'll call Tij to be Wij plus W I minus 1 J plus 1 minus, so just swap this I J plus 1 I minus 1 J, Okay, so the idea is that this is mostly going to be equal to alpha ij, mostly because it's going to be equal in the range of interest, but outside that we're not too interested, so but it may not necessarily hold. So for 1 less than or equal to I equal to j less than or equal to n. Okay, so looking at based on the categories for alpha ij. So for this first category, Tij, so j is I now, so this would just simply be wi minus 1 I plus 1 wi I plus 1 wi minus 1 I. Okay, so we see that we need for wij we need I to be greater than or equal to j, otherwise it will be 0 by definition. So most of these terms are actually 0 based on that inequality. I'll just get wi I. And for wii, looking at the definition for w once more, we'll sum over all the case from j to I, so that will be just from I to itself. So just have mu I squared. Okay, so this is just mu I squared, and mu is plus or minus 1, and if you square this we just get 1. Okay, so this one is the same as alpha ij. So far so good. Now for the second class, 1 less than or equal to j, strictly less than I less than or equal to n. Tij, so we have so let's look at this closely. So all this will fall under the green range, the green inequality, except possibly for the second term here. That happens when I minus j is exactly 1. So when you look at that, it may not necessarily hold, but if you observe for this inequality, when j is I plus 1, then by normal definitions this summation actually makes sense, and it's just the default 0. Okay, so we're just going to still write it in the summation form. So we're just going to write everything based on what we expressed. So this is a normal one, mu I mu k. So this, we're taking this squared. Now for this one could be empty if I is equal to j plus 1. So, and that's the only time it's actually empty, and that will just be 0. So this is still actually well defined. So we'll write it that way. K j plus 1 I mu k. Okay, so this time k j I minus 1. So I'll call this just call this x. Then this would be mu j plus x plus mu I. So it contains the first and the last term, I and j, and then the others, if they exist, that will just be x. If they don't exist, that's just 0, and it still makes sense. So we do the same here. Here we don't have j, so just x and mu I. Here we have j and the remaining ones, and they don't have I, so this is what we get. So this is actually going to be equal to this squared. Now I'm going to use difference of 2 squares simplify, so I'm going to take the third term and shift it forward a bit. Okay, and then we have x squared, we have okay. So now we take difference of 2 squares, so we'll take the difference first. That's mu j, and we'll take the sum, 2x 2 mu I, and here we also take difference of 2 squares. So difference now is actually looks negative, minus mu j. Then we have mu j and that's the sum now, and 2x. So we can pull out mu j, and once we've done that, this would just be 2x 2 mu I minus mu j. So minus go through, and then we have minus 2x as well, and some things would cancel. So this just gives us 2 mu I mu j, and this is also equal to alpha ij in that range. So these are the two important bits, and this is the important range. Outside this range, we're not really worried about this because hij will be 0. Okay, so this means we can actually conclude that alpha ij hij is actually always equal to this. This is now for every I and j integers. So in the right range, they are both exactly equal, but outside that range, hij is already 0, so both sides are also equal to 0. Okay, so this is what we get. So we're going to use, instead of taking the sum over alphas, we'll take it over the t. So this means looking at this sum, j z. So this is the original sum. I want to show this is non-negative. So this is the same as j tij. Okay, so remember what tij is up here. So we're going to use that wij, wi minus 1, j plus 1, and so on. So this will be, so we're just going to divide it according to those categories: wi, j, hij, w. Okay, so that's wi minus 1, yeah, so I minus 1, j plus 1, hij, and minus I z, j and z, w I j plus 1, hij. So to simplify this, we'll be using this is the reason why we looked at the entire z instead of just being very specific. It's going to be easier working on it this way. So this is just this. So what we're going to do is now just change our variables. So just change the summation variable. So we're just summing over all integers. So this is wi, this is I. So we could just change this to a new notation, like maybe k or something, but I'll still call it I. So the red I. Now after I, we have I minus 1 here, and we have I here. So if we change this first one to I, this should be the next number, and that will be I plus 1. That applies here. And we can do the same for j. Down here, I can call this j, and then this will just be j minus 1. So we're just changing what we're considering as the summation variable. We apply that everywhere. Okay, so we apply this everywhere, and this is what we get. Now once it comes to the summation, since we're summing over all integers, now we don't need to worry about the range anymore. So just shifting them with plus or minus 1 will still just be the whole set of integers. So this is the main reason why we looked at the entire set of integers rather than just being specific from 1 to n. So both ways work, but I think this is better. So if we do that, we still have the same sort of sum. Now everything will become wij. What would change now would be the h. So we'll just factorize that. Now these are finite sums, by the way, so just keep that in mind. Most of these terms are actually 0, so they don't exist. So we have this, but they don't have this j minus 1. We have this j minus 1 and I plus 1 j. Okay, so this is what we get, and this is exactly the condition we stated for h. Now just that this condition is not for every ij, but for I greater than or equal to j, right? So this is greater than or equal to 0 for I greater than or equal to j, and this is greater than or equal to 0 every time, but equal to 0 if I is less than j. So that's w. Remember, w is good in the green region, but outside that is 0. So if I is less than j, then that's also 0. So if I is less than j, because of w, this neutralizes the entire term, and then otherwise we just have that both terms are at least 0, and multiplying we get a non-negative number. We sum over all this and we conclude that it is non-negative. Okay, so far so good. So we've proved this lemma. Very important. So we're going to use this now to try to apply to a certain class of function. So we're going to work out what class of function we really want to deal with. So start by defining a function and bringing in a sequence. So let f be a function from s to r, so where s is this region of the xy plane. So xy such that 0 is less than y is less than or equal to x. Okay, so I'm going to give a sketch of this this region. So it's kind of like a triangle, half of a quarter plane, so to speak. So let's go with this. Okay, so this is a sketch. So this is like the x-axis, y-axis, and then we have this. So based on the equality possibilities, we can make it straight. Yeah. So it's just this region here. So it's about 1/8 of the plane. Okay. All right. So function is defined on this region. Then next we look at sequence. The sequence is actually the same sequence as in the problem. Let's x1, x2, xn be reals. Okay, so this is all we know. So now we're going to adjust this to our liking. So we're going to permutate, take the absolute values of this and then reorder them. So let's x1 prime, x2 prime, xn prime be a permutation of the original numbers, such that 0 x1 prime is greater than or equal to x2 prime. So just take them in decreasing order to the last one. Could have equality greater than or equal to 0. Okay, so we have this, and then now we use the lemma, but to do that we need to make sure this is well defined. So this is what this is a proposal. So we have hij is f of xi prime xj prime. Okay, so this is for this makes sense based on the sequence we've defined for I and j between 1 to n, but also for f we need x to be bigger than y, as in s. So xi prime has to be bigger than xj prime, and since we've ordered this, it means that we have this. It makes sense for I greater than or equal to j. So let's say j less than or equal to I. Now, since we're also dealing with this sequence, the numbers have to range from 1 to n. So this is just the same as our green region. Just going to shade this again. So this is the region of interest, and that's why we're so particular about this. So far so good. Now, but h is supposed to be defined everywhere on z cross z. So going by the second condition of h, which is just saying you can just set it to be 0 everywhere else. So just take that as a natural definition. So this is 0 for otherwise. So based on this, there's no problem with f. It's now about the first condition for h. So we need this condition to hold for I greater than or equal to j. So for h, well defined, so h to be well defined, must have h I j plus h I I plus 1 j minus 1 minus h I j minus 1 minus h I plus 1 j to greater equal to 0 for all I, that's all j less than I, integers. So I must have this everywhere. Now if I and j are in the wrong range, if they are not in the right range, then h would just be 0, so this would just be naturally correct. So the part we need to worry about is where things could be in this range. Now when j is less than I, then the coordinates for the middle inequality, they all work out. So if I is bigger than or equal to j, then I plus 1 is also bigger than or equal to j minus 1, and so on. So those parts, they are fine. So it really just comes down to the boundary conditions. So so you could have, if j cannot be negative, sorry, j cannot be 1 if j is, sorry, j cannot be 0 or less. If j is 0 or less, then all this will just be 0 or negative, and they all defy the range for the non-zero parts. So all this will just be 0. So we're rather interested in where they might not be 0. So we want them to be in the right range. So we don't want all of them to be in the wrong range. So if one of them is in the right range, that's just fine. So when j is 0 and below, this fails. The same applies when I is bigger than n, because I plus 1 would be even bigger. So this fails. So we consider the range j from 1, and of course we already have this, and then up to n. So we still consider this range. So otherwise what we just did is all terms will be 0. Okay, so these are where we might have some terms not being 0. So we want to see what it takes. So now if j is 1, some terms might not necessarily be 0, but some other terms will be 0. So the extreme boundaries are also quite peculiar. So we're going to take 4 cases. So case 1 is where j is 1 and at the same time I is n. Okay, so when we have this, then we get h, let me just write what we have. So most of these terms they are gone, right? So just strike them out. There'll be 0 because of they don't fall in the right range. You can see 0 here, n plus 1 here. So we just have the first term. So I'm going to write what that means. So this is the same as saying f of xn prime x1 prime as okay, sorry, I think I made a mistake somewhere above. Why we reordered these terms? Okay, so when we reordered these terms, okay, so this will be less than or equal, so we want this to go in order. Place a 0 here. So I want this to go in order. I think I flipped it. Yeah. Okay. So sorry for the confusion that might cause. All right. So I just want the higher subscript to feel higher as well. Okay. So we have this. Is greater than or equal to 0. Okay, so we'll come back to this and let's look at another case. So there are 4 cases. So case 2, so j is 1, but now I is less than n. Of course, I has to still be greater than or equal to j. Just take that as a natural assumption. Okay, so this will be h I1 hi plus 1 0 hi 0 hi plus 1 1. So once again, some terms are 0, but a bit more now. A bit more terms are not 0 now. So this will go, and the other 2 are actually fine because of the range we're dealing with. So this will also translate to some condition in f. That's a h of x I prime. So this has to be greater than or equal to 1. Is x1 prime is greater than, so taking the other term that way, we have this. So this is what it translates to. So the next case would actually be similar. So this time I is n is greater than j, which is strictly bigger than 1 this time, and you have n j, n plus 1, j minus 1, n j minus 1, n plus 1, j. We'll cancel some terms out. The ones with n plus 1 are out of range, so we'll cancel them out. I'll just write based on what's remaining. We'll do the striking later. We have x n so xn j prime greater than or equal to f of x n prime j, so this one j minus 1. Okay, so this is what we get. Alright, so let me strike out what should be struck out. So we have this one and this one gone. Okay, so the final one. So beyond this is a more general range. So we've left the boundaries completely. So the inequality, no term would naturally cancel out. So here we have this strictly less than 1, less than I, strictly less than n. So once we're in this range, we just have inequality that goes as follows. So just change each of these to their x components and the f. So we have this. So I'm going to write it in a particular fashion. Okay. Let's see the best way to do this. Okay. So I'm going to write this. I want to write it in a particular fashion to be more useful. So just change some of this. Okay. All right. So we have. I'm going to use I plus 1 first, and j minus 1 here, minus f of xi prime xj minus 1 prime greater than or equal to, so take the others this way. It's not the only way we could go about this, but let's just go with this one. Okay. So we have 4 inequalities. We need all this to hold, and we actually just want, since we not specify, since it was not specified about what real numbers these are, so we want this to hold every time. So we want this to hold for every real numbers. So but for what we have here, they're already ordered. So this is we're going to write it. I think we just rewrite this. So basically there are 4 points. So I'm going to write it as follows. So f of ab greater than or equal to 0 for a bigger than or equal to b. F of so let's say, trying to reorder this. Okay, so we can write it this way: f of ac for a greater than or equal to b greater than or equal to c. So the a here is like xi plus 1 prime, and the c here is just x1 prime, right? So second one would be the third one rather would be a b and a c, so the same range. And the fourth one, we can also order this 4 times. So this one is the biggest, then followed by this, and then this, and then finally this one. Okay, so we just call them A, B, C. Okay, A is the biggest one, so this will be like A minus D, B minus D, A and A comma C, B comma C, and this is for A greater than B, greater than C, greater than D. So now, for the sake of progress, we can assume that this function is kind of smooth, so differentiate as many times as we might need to. So we're just gonna assume that. So if we do that, then these conditions can be translated into whether the function can picture it as whether the function is increasing or decreasing. So for the first one, just means that f is always greater than or equal to 0. So write it this way. For the second one, now we see that the second coordinate c is fixed. So if you assume the second coordinate is like constant, then this now simply means that the function is actually decreasing, because we have a greater than or equal to b, but we have f of b first. So this means if we take the derivative respect to the first coordinate, so the second one is fixed, so that is fx, that's which is the partial derivative of this respect to x, then this will be negative because it's decreasing. Okay, and the next one similar but different. So this time, if the first one is basically fixed, picture it this way, and we're taking derivative based on the second one, so fy, which is partial derivative respect to the second coordinate. Now this time it is actually increasing, so this is bigger than 0. So this is what this translates to. They are equivalent, so it goes both ways. For the last one, to look at this very well, we're going to have to consider a new function. So I'll call it f1. Okay, now let's say f okay, this would be f ab of x, or rather of y. Let's call it this function. That's for y less than or equal to b. Okay, so if you do this, then this function, because we can plug y to be d and c, we'll see that this function is decreasing. So it's decreasing once we are less than b. So in terms of derivative, is basically if we take f prime y, so this should be less than 0, and taking the derivative with respect to y is just taking second derivative here. So we must have that this is true for all a greater than b greater than y. Okay, so rewriting this now is the same as writing this. So I'm going to write this as a more general stuff. So call it t. It's greater than fy. So this may not necessarily be strict, so let's not make it strict. So depending if it's strict, then the following equalities might be strict as well. Anyway, so we have a t. So this is for every a and b bigger than t, where a is bigger than b. So this is now, we can picture this now as a function. A function where t is fixed, right? So if you look at this as a function where t is fixed, then this function is now decreasing. So this function is decreasing, so it means that fy, this t, is decreasing for, so let's call it x, for x bigger than t, so in the region s greater than or equal to t. Okay, so that's the interpretation of this. In terms of derivative, that just means that if you take derivative with respect to the first coordinate, so that's fyx or xy of xt is going to be less than 0 for all x greater than or equal to t. Normally x is greater than or equal to t, so this just simply means in the for the values where the function is defined, this is negative, so we get fxy, which is this. Doesn't matter which one you actually take first, you could arrive at the same conclusion. So this doesn't have to be strict. Okay, so this is what it takes for h to be well defined based on like what we defined it here for and how we used it. So any function that satisfies this is good to go. So just need f xy to be greater than or equal to 0, fx is greater than less than or equal to 0, fy greater than or equal to 0, fxy less than or equal to 0 over xy. Okay, so this is what we need here. I'll highlight this a bit. So once we have this, then we're basically good to go. So it just remains to define one more thing, which is the sign. Then we can apply the lemma 1. So now whatever function we're dealing with f, we're going to be assuming it also satisfies this condition. Okay, so don't have to state it anymore. We'll assume this is true. Okay, because it's necessary. So now going back. So to look at lemma 1, we need to know what alpha ij is, and that is defined by mu. So in this case, we also need to define what mu would be. So mu is just going to simply be the sign. So define mu to plus 1 or minus 1 to be so it just takes I and gives it the sign of xi prime. But xi prime is when we've ordered this. So once we've ordered this, look at the sign. Now if xi prime is 0, we could just take the sign to be 1. It's not very important. Any of the sign actually goes for this. So otherwise we just use our regular sign. So if it's positive, it's plus 1. If it's negative, it's minus 1. So this is what we'll be taking as our mu. And once we have this, then the function, the lemma 1 holds. So we don't get lemma 1. So we're going to interpret lemma 1 in terms of this definition of h. Okay, so that's in terms of our sequence. I'll be going by this second expression for lemma 1 since it's not an infinite sum. It's a sum within a certain range of interest. But I'm still going to write it based on the first notation, but most of the times will be 0. So to make things very smooth, now let f xy okay, so let me do this properly. So I need to do this properly. Okay. Alright, so to do this properly, we take a new function, so we just call it f cap. So f cap will be defined based on the previous function. We could go to and fro, so it's going to be now from r cross r to, now f has to be positive, but this function we're dealing with doesn't have to be positive. So it's just going to be r to r, so it's very free function. So it's going to be defined by f xy to be sine of x times sine of y times f of the maximum of these two, then the minimum, so because we need the first one to be bigger, of these two. So we're going to define f bar this way. If we have this as our definition for f bar, we could retrieve f from such an f bar, but to do that we need to just observe a few things. So we observe that so once the function satisfies this property, then it's going to be easy to extract the original f back. So if we swap x and y, we get the same thing, so it's symmetric. That's because we're taking the maximum and the minimum will remain the same. And also in terms of the sign, because we took absolute value, so those are the two important details: maximum and minimum. It captured the symmetry. Then the absolute value of x, y, and then the sign together with that. So it's just about positive and negative values. So if you take minus x, this, then the absolute value parts will remain the same except the minus coming out. So if we have this, and also the final one, if we swap so there's no need for writing this other one. That's because it's already symmetric, so this applies in both dimensions. Okay, so we must have these two properties from this function. That's alongside the differentiation properties we already had before. And apart from this, we also need f. So I'm not going to write the differentiation parts of things, that is the derivative parts, but I'm just going to include briefly this first part. So this is this for x comma y positive, okay. Alright, so now any function that satisfies this and of course the relevant derivative properties, then we can just quickly extract f of x comma y by just taking just having this. So this will just work out nicely, because for this to be well defined, it has to be in this range, and for that range the maximum is well defined, the absolute value is well defined, the signs are well defined, so it just become equal. So it's easy to extract the f once the writings are satisfied, and then we'll have the right function. Okay, so we'll be working with f cap, and that's the version we'll be rewriting the lemma 1 in terms of, so just call it lemma 2. Okay, so lemma 2 would be more like saying summation I from 1 to n, summation j from 1 to n, f cap of such a function xi and xj is greater than or equal to 0 for all real xi. Yeah, up to n. Okay, so to prove this, we just use our lemma 1. So we have this okay, so I'm gonna write it this way. So let's start from the left hand side and work our way through. So we'll start with this. Now here we're just summing over all the xi or the xj independently. So doing that, we can just pick the order which we used in our permutation. So we'll now be taking this as xi prime, xj prime. So just use the ordering, not necessarily the order from the original sequence. So this is a permutation now. So we have this. Okay, so once we have this, then knowing about I and j tells us about the absolute, which of the absolute values are bigger. So we can translate this to f directly, which would be 1 to n, 1 to n. Now this would be the sign of xi, that's just mu I. Sign of xj, that's mu j. And we now have f of maximum xi, xj, and then the minimum of those two. Okay, so we'll now take this in so since it's symmetric, we can actually look at this as saying we're looking at I think probably could have done that earlier. So if I equal to j, this is just the sum of this. That'll be mu I squared f of, so the maximum minimum, they both be the same, so no difference. Or since it's symmetric, this will just be 2 times when we take sum from 1 to n, but we can now be specific and let I be the bigger one. So I bigger than j strictly. So without loss functionality, I is bigger than j. So you can say j less than I, and still run between this range. Now we'll have this, and now the maximum will be well defined, which would be xi and xj here. Okay, so once we've done this, this is just one. This is h of I. This here is h of ij, because of they are in the right range, and so this is the definition. And 2 times this part give us alpha ij for that range, and this is also alpha ij for this range. So this comes together nicely as summing j less than or equal to I less than or equal to n of alpha ij hij, which is just the same as when we took this over all z. And this is greater than or equal to 0 by lemma 1. Alright, so yeah, that was a bit of work. Alright, so this is the main stuff. Any function that satisfies this, then this should be greater than or equal to 0. I'm sure you already seen where this is going to. This is very close to what the equation requires. Just the f cap will now just be simply when we swap these two, we take everything to one side and place it in the summation notation, and it's easy to verify that it satisfies the right properties. But we're not going to stop here, so just going to do something a bit more extra. So this is the main stuff. We're done with the main stuff. So we're just going to explore a bit more about what it takes a function to satisfy the properties for f, not of f cap. So for f cap, you just need to check some symmetry stuff and then some stuff about the sign, and yeah, then that relates us back to f. So it's strictly about f, and we need f to be on what to be defined on the set S, properly defined on set S. Yeah, and not just defined on set S, it must satisfy these conditions. Okay, so this condition is kind of like a geometric aspect to the shape of the function, but it's not as simple as saying whether the function is convex or concave, but we could try to relate this to another function. Okay, so let f, so let's G be a set from a function from S to R. This is going to be R plus, so R greater than or equal to 0. Okay, such that such that f of xy, well, let me use s and t here. So f of st will be equal to g of s plus t, comma s minus t. So this is well defined. The reverse of this would be, which is more straightforward stuff. So this would be the new s, the new t. So to get the previous s, we add this 2 over 2 to get s, and then we subtract by 2. So this is well defined because for this one we need s to be greater than t to be greater than or equal to 0. That's based on t, s comma t, since s comma t is in s, so it's in that range we described earlier, and this will imply that, so it goes both ways, that this is also in s, that is this is greater than or equal to s minus t is greater than or equal to 0. This part is just like picking out the t greater than 0 part and switching some stuff up when you cancel the s, and then here it's just the same as the other one, so it's just like swapping the inequalities. So when one value is in the set, the other value is also in the set, so it's just very well defined. Okay, so meaning we can rather write the function in terms of sort of g, and be using this relationship especially. Okay, so f greater than or equal to 0 is the same as g greater than or equal to 0, and we've covered that already. Now fx of st has to be less than or equal to 0 from the conditions we're working with, and if you take the derivative now, so that's g, so we have to be a bit careful here because there's some change of variables involved. So we are differentiating this with respect to the first variable, and so that is respect to s. So differentiate this with respect to s, it's supposed to be less than or equal to 0. So this now would be so some sort of chain rule. Differentiate the first part with respect to s, we get 1, so we get this plus, and for the second one we still get 1, so gy and the same stuff. So this is less than or equal to 0, so that's what this becomes. Fy st, this one has to be greater than or equal to 0. Everything will be similar, but not exactly the same. So this time we're differentiating with respect to the second one, which is t, and that will be, for the first one we still get 1, so this part is the same, but for the second part, s minus t with respect to t will be minus 1. So get this greater than or equal to 0. For the last part, which is x, y, st equal to 0. So differentiate both of these. So what we could just do is just write this first as st s minus t ds dt. So we could just differentiate the this one respect to t again. That would give for the first part will give 1, so that's gx x st s minus t. Second part now respect to t will give -1, so that's gx y, the second part. This now for gy we get respect to the first part gy x s plus t s minus t, and the second part just get the same. So this is less than or equal to 0. So this is less than or equal to 0. And these two are actually the same, so just gonna strike them out. So the conditions become g greater than or equal to 0, gy. So the terms within are not really changing, so you can just change the variables back. So g is greater than or equal to 0, gx plus gy is less than or equal to 0, gx is greater than or equal to gy, and finally gxx plus gyy is less than or equal to 0. So it's not looking as nice as the other one, but we could use this to have a few examples of functions that satisfy this, a whole class of functions that actually satisfy this. Okay. So from this we could actually combine these two into one inequality. This will create a bound on gx, so that's gx is greater than or equal to gy but less than or equal to minus gy. So this means minus gy has to be greater than or equal to 0, less than or equal to 0. So gy have to be negative, and not just that, but is when we take the negative value of that, going to get that is bigger than gx in absolute value. So in essence we have gy is greater than gx in absolute value, but gy is less than or equal to 0. So that's what those two conditions come down to. So the first class of functions we'll just consider briefly would be a function, let's call it v. So this function v from r, should I say r greater than or equal to 0 to r greater than or equal to 0. Where we take gxy to be vx minus vy. So this is the structure of this current problem, where v is just square root. So if you plug v equal to square root in this and go back to original f, you just get what we want. So that is fxy, which is g x plus y x minus y, will be v x plus y. So this is what we have. So this is just a very special, the question is just a very special case of this one. Okay, so now we just need to check what this function v needs to satisfy. So g greater than or equal to 0 is if only if v of x greater than or equal to v of y whenever x greater than or equal to y. Okay, so this is just matter of saying that v is increasing, so we can just say v prime is bigger than 0. Okay, so that's what the first one breaks down to. The second one, or the next two, so we have g of y is less than or equal to 0. Gy, when we differentiate respect to y, is less than or equal to 0 always. So gy is equal to the first term of vanish, we have minus v prime is less than or equal to 0. So this part is fine, we already had this before. Now when we take the absolute value, so that's this bit, so we have gy is greater than gx. So this is when we differentiate and take the absolute values, so note that v prime is already positive, so we get v prime of y here is greater than or equal to v prime of x for, once again, x greater than or equal to y. So this time it means v prime itself is decreasing, so if you take the derivative of v prime, which is v prime prime, but less than or equal to 0. And we'll see that this actually guarantees the last part we need to check, which is this less than or equal to 0. So if you differentiate respect to x twice, we get v double prime x. Differentiate respect to y twice, we get minus v y. Just a moment. Oh, I think I made a mistake somewhere. Felt wrong. When we're differentiating this respect to t, this should be minus as well. So this is minus right here. Yeah. So this should be minus. Okay, yeah. So this should be minus. Sorry about that. So this is minus. We'll take g respect to y twice. We get minus v double prime y. So minus and minus will cancel out to give plus, less than or equal to 0. But we already know v double prime is less than or equal to 0, so this part is also natural. So it all boils down to just two things. In other words, for the first part, we could describe it as saying that v is increasing, and the second part is that it is concave. So if v is increasing and concave, then we're done. So in particular, when v of x is square root of x, then it works because square root, just say from a sketch, this is not necessarily the proof. You could just differentiate this. So this is square root of x, so it's concave and it's increasing, so it's perfect. So this solves the problem. Just another class we might consider, but for this class it's a bit tricky because when we look at some boundary conditions, things might not converge nicely. But just curious about other functions that might satisfy this, apart from functions of this structure. So another class of function that actually just by observation satisfies this is gxy equal to x raised to power alpha y raised to power beta, where alpha is greater, where beta is greater than or equal to alpha is greater than or equal to 1. So for this one, just simply need to differentiate and you can see it coming out. Okay. So it's certainly for the range of values we're dealing with, it's certainly positive. except at the boundary, as where y is 0. So that's part of the tricky parts. Then g of x. So this inequality here, we're just going to look at this inequality. Yeah, so gx will be x alpha minus 1. We have this, and gy is minus beta x is yb plus 1. So g is certainly negative. Alright, so that part hasn't sorted out, and then when we take absolute values, so gx is going to be greater than or equal to this, so just check. So looking at their positive versions, cross multiplying and cancel out some relevant things, we get this. Let's see, this is right because we're trying to prove. Okay, should be the other way around. Okay, so this is y, and then here we'll have 1 x left. And if x is bigger than y, and also if we assume beta is bigger than alpha, then indeed this will hold. Okay, so that's true. Since alpha is less than beta and y is less than or equal to x. Then finally we'll look at g double x. And g double y this time becomes positive again. X alpha y beta plus 2. So just to confirm, we want to prove that g double x is less than or equal to g double y. So I want to confirm this, which is alpha minus 1 so based on the range of values we're dealing with, these are both positive, so you just assume y is not 0. Cross multiply, that gives this y squared x squared. So this is also true, since beta is already greater than or equal to alpha, they're positive. Beta plus 1 is strictly bigger than alpha minus 1, then x squared is bigger than y squared, so this works. So this gives us our function. So we could just plot this to see how it looks like, but yeah. Alright, so that took a while. Thanks for being part of this lesson. Yeah, so we'll see you in the next one. Bye.